You ever notice how just one little piece of new information can totally change the game? Think about it. A surprise witness in a trial, a star player getting injured right before a championship. All of a sudden, everything you thought was certain is up in the air. Well, today we're going to crack the code on exactly that. We're talking about conditional probability. All right, let's jump right in with a real-world puzzle. Picture this. It's election night. We've got the exit poll data from 1,000 voters. And what we're looking at here is a table that breaks down their votes. Did they pick candidate A, candidate B, or just submit a blank null vote? It also splits everyone up by gender, and it's a perfect split, 500 men and 500 women. So let's start with a really simple question. If we just close our eyes and pick one voter at random from this whole group, what are the chances they voted for candidate A? Well, we just have to look at the totals. We see 400 people voted for A out of a total of 1,000. So that's 400 divided by 1,000, a nice clean 40%. Easy enough, right? Okay, but here comes the twist. What if we get a clue? We're told that the voter we picked is a woman. Now, does the probability that she voted for candidate A stay at 40%, or does this new piece of information, this condition, change the whole calculation? And that question, well, that's what this is all about. You know, the key to solving this isn't some crazy, complicated formula you have to memorize. It's actually a really simple but super powerful shift in perspective. It's all about learning what to focus on and, just as importantly, what to ignore. So here's the absolute core idea. Once you're given a condition, in this case, knowing the voter is a woman, you are no longer dealing with the entire universe of 1,000 voters. That whole world doesn't matter anymore. Instead, your entire world shrinks. Your focus narrows down to a much smaller, much more specific reality. You're now living in a world that only includes the possibilities that actually fit your new condition. And you can see that idea perfectly right here. Since we know our voter's a woman, that entire row of 500 men, it's gone. It's totally irrelevant to our question now. Our new, smaller universe is just these 500 women. That is our new total. So now, we ask the question again, but only inside this smaller world. Of these 500 women, how many voted for candidate A? The table tells us it's 180. So the new probability is 180 divided by our new total of 500, which comes out to 36%. The new information definitely changed the odds. It dropped the probability from 40% down to 36%. Now, this slide gets at the number one place people get tripped up. There's a subtle but huge difference between two questions. The probability of picking one person from the whole group who is both a woman and voted for A. That's 180 out of the original 1,000 people, which is 18%. But the probability that a voter chose A, given that we already know they're a woman, is 180 out of only the 500 women. That's 36%. See the difference? It's all about which total you're using as your base. Tables are great, but when things get a little more complex, like a sequence of events, we need a better tool. So let's talk about probability trees, which are basically a visual roadmap for solving these kinds of problems. At its heart, a probability tree is just that, a map. It shows you all the different ways a situation can unfold, step by step. Every time the path splits, that's a different possible outcome in a chain of events. But here's where they get really powerful. We can add probabilities, or weights, to each of those branches. And when we do that, our simple map turns into a dynamic calculator that shows us exactly how likely it is to travel down any specific path. And using this calculator is surprisingly easy. There are really only 3 rules you need to know. First, all the branches that split off from a single point have to add up to 1, or 100%. Makes sense, right? Second, to find the odds of one specific path happening from start to finish, you just multiply the probabilities of each branch you took along the way. And third, if there's more than one path to get to a certain outcome, you just find the probability of each of those paths and then add them together. That's it. So we've seen how getting new info can totally change the odds. But does it always? I mean, are there times when two events are just completely separate, where knowing about one tells you absolutely nothing about the other? Let's head back to our election data and find out. This time, let's look at a different relationship. Let's see if there's a connection between a voter's gender and the chance that they submitted a null or blank vote. Okay, first things first, we need a baseline. So out of all 1,000 voters, a total of 170 cast a null vote. That gives us an overall probability of 170 out of 1,000, which is 17%. Simple. All right, now let's apply our condition. We'll shrink the universe again, down to just the 500 women. Within that group, how many submitted a null ballot? The table says 85. So what's 85 divided by 500? It's exactly 17%. Wow. In this case, knowing the voter was a woman told us absolutely nothing new. The probability didn't budge one bit. And there's a name for this. This is what we call independent events. It's when two things are completely unrelated in terms of probability. Knowing that one happened doesn't change the odds of the other one happening at all. Or to put it in the math terms we've been using, the probability of A given B is just the same old probability of A. But here's a quick, really important warning. Don't confuse independent with incompatible. They're totally different. Incompatible events are things that can't possibly happen at the same time, like flipping a single coin and getting both heads and tails. Independent events can totally happen together. They just don't influence each other's odds. Okay, so let's pull all these ideas together and look at a really high-stakes scenario where our gut feelings can get us into a lot of trouble. I'm talking about interpreting the results of a medical test. So here's the setup. We've got a pretty rare disease that only affects about 2% of the population. A new screening test has been developed, and it seems super accurate. It correctly identifies 98% of people who actually have the disease. And for healthy people, it almost never gets it wrong. It only gives a false positive 0.5% of the time. Sounds like a great test, right? This is the perfect kind of problem for a probability tree. You see, the first split is simple. Is a random person actually sick or are they healthy? Then, from each of those branches, we split again. Did their test come back positive or negative? This lets us map out every single possibility. And now, here it is, the big question. You go in, you take this test, and it comes back positive. So, based on everything we know, what is the actual probability that you are sick? Now, your gut, your intuition, is probably screaming 98%. I mean, the test is 98% accurate, right? But is that the real answer? The answer, believe it or not, is nowhere close to 98%. Our intuition completely fails us here because we're so focused on the test's accuracy that we forget about how rare the disease is. To get the real answer, we have to reverse the tree. We need to compare the probability of being sick and testing positive to the probability of anyone testing positive. So using our tree, the chance of being sick and getting a true positive is about 1.96%. But there's also the chance of being healthy and getting a false positive, which happens about 0.49% of the time. The actual probability you're sick is that first number divided by the sum of both groups. And when you do the math, the true probability is only about 80%. This reversal is the ultimate power of conditional probability. It helps us fight our own biases and see the true odds, especially when the stakes